Okay, all right. Today we're going to continue on with the lecture. We're going to go over nebular theory. I've got a couple things written on the board. It shouldn't be too bad. It's taken me longer in first period to go through stuff. I might get a little bit ahead of where we left off first period, but we're kind of getting to the point where we'll probably finish on the moon today. Tomorrow we should be able to go through all the planets. Maybe end with Pluto. If not, we'll say Pluto for Friday. But we should be through this chapter and on to the next chapter by the end of the week. I will be getting your homework out to you in some form yet. I don't know what format that's going to be in Canvas, but everything needs to be in Canvas this year. Also, I'm going to try to put in a test on Canvas to see if the lockdown browser works for y'all's Chromebooks. Because if it works for your Chromebooks, that's going to make the test much easier to create in a better way for y'all. So the online students at home, talking to y'all, don't have an unfair advantage that y'all would not have here in class. Because obviously, there's no one there to watch them. So a lockdown browser would help for that. More than likely, let's be honest, the online students are going to have access to their books and their notes. And so the tests this year, which I've done previously, are going to be open book, open note. So I just want to say that and get that out there. So if you're a note taker, you can take your notes on the computer, but make sure that before a test, you kind of get them into paper format. Because if the browser's locked down, you're not going to have access to those. If you're a paper note taker, you should be good. Just make sure you have those with you. That being said, the tests are pretty much going to be designed in a way where if you're looking things up in a book, your notes might be super helpful for you. But if you're having to look things up in the textbook, it's probably going to cost you more time than you need. So make sure you're paying attention and kind of understanding some of these things. And if you have questions about something in class, if we don't get to it in class, shoot me an email. I should be able to explain it to you through email. But we're going to keep pressing forward. Pretty soon here, we're going to get through this second chapter. We're going to have a test. And then once we get to minerals, we're going to start to have labs. I don't really have a space lab for us to do. So we won't have a lab in this first section, but we'll get to labs pretty quickly here. Now you're in the video. Everybody heard it. So we're going to start off today with nebular theory. And one thing that I want to talk about before I get into the PowerPoint is how so nebular theory is our understanding of the way that our solar system formed. And really it comes down to the interaction between matter and gravity, which is the realm of physics. And until proven otherwise, physics works in the same way in all places in the solar system in the universe. And so we are talking about solar systems for this nebular theory. Know that this also extends down to planets. Planets form in a very, very similar way, especially if you're looking at planets that have rings like Saturn. It also extends upwards in size to galaxies, especially if you're talking about like a spiral galaxy. And so this concept of compaction, spinning and rotation, and then kind of solidification and cleanup are scalable up and down in the universe. And so we are just going to talk about solar systems, although planets are inside the solar system. But it does kind of work the same way for galaxies and how galaxies are materialized in a way. So nebular theory, does anybody know what a nebula is? Just a basic definition. A nebula is a gas cloud. And if you think back, I'm not going to go back to it because it's not super easy to navigate in this. Wish I had a keyboard up here. Maybe I need one of those like pointers that let you move forward and back in the slide. I actually have one. Maybe I need to bring it. Sorry. A nebula is a gas cloud. And so earlier in the PowerPoint, there's a picture on the left side here that was the God's Eye Nebula. And it's just a big gas cloud out in space. And by gas, it doesn't necessarily have to be all your lighter materials like it would be gas here on Earth. It can be heavy, rocky materials like iron. They're just at the molecular level or very, very small level, and nothing's like condensed. And so it's just matter that's floating around in space in a cloud form. And so what happens from there is what we call the nebular theory. It's how planets form. It's how our solar system forms. And it is something that kind of follows the rules that we know about gravity and about matter. So before we go through this, because this PowerPoint doesn't super explain it well, I have a couple pictures which illustrate it a little bit better. So let's go to this one first. Actually, no, sorry. Let's go to this one first. You have your gas cloud here, which they illustrate right here. In any cloud, you're going to have a center, and that center has a couple advantages to it. First off, as opposed to the edge, particles in the center are surrounded by a lot of other particles. And as they move around randomly through space, they're more likely to collide with other particles. In space, well, not in space, but everywhere, period, everything, no matter how small, even an individual atom, has its own gravity. Now, the very small pieces, the gravity is very, very small. And on Earth, it doesn't really matter because it's all overtaken by Earth's gravity. And so you never really see anything small interacting with a gravity-like tendency. But in space, where there is no other force acting on it, gravity is very important. And in the very center of this cloud, you start to get particles that, as they move slowly, they bump into another particle, and their gravity kind of pulls them together, and they stay together, or at least in a general vicinity. Now, if I have two particles that are together, they have a little bit more gravity than one particle, and so they're going to pull in a third. Now, those three particles have even more gravity, and it just gets more and more kind of like a snowball effect, where the center starts to coalesce, things start to come together, your gravity increases, which pulls more things into it, and pretty soon you have a somewhat more dense clump in the center than anywhere else. It starts to create a bigger gravity field, and it starts to kind of react everything and start to pull it in. Now, the step from step A to step B, which they show here, is the one that I'm going to be able to explain with the least detail to you. It's something that I need to learn more about. It isn't a very advanced concept. It's more physics than Earth and space geology. But essentially, as you have this coalescing and things moving towards the center of the galaxy, they have momentum. And at some point, that angular momentum is conserved, and it results in a flattening and a spinning of that gas cloud. Now, the physics behind that's going to be hard to explain. It would be unnecessary to explain in this class and take a very long time. Know that they're there. You can probably find a YouTube video or a TED Talk that explains it pretty well. I'm actually going to attempt to do that this year and see if I can find something, and I'll post it on Canvas for you if I do. But this is something that we see happen over and over and over again at all three scales, at the planetary scale, the solar system scale, and the galaxy scale. You get this flattening and you get the spinning. Okay, so conservation of angular momentum pulls the cloud into a disk, and that disk begins to rotate. And this rotation is important at the solar system scale and at the planetary scale. The central mass starts to form, so the part in the middle that got the most gravity the first, at the very beginning, not the first, the most gravity at the beginning gets the most material. And as more and more material comes in, just like any planet, the very center is going to start to get hot. You have a lot of pressure. That pressure relates to heat, and it really starts to heat up. This is going to begin to form your proto-sun, the very beginnings of your sun. You also have a nice flat disk towards the outside that's spinning and contains a lot of other materials. So as this disk is evolving along with the proto-sun, this angular momentum does something very interesting. The lighter particles, like your gases, your hydrogen, your helium, your carbon, they're going to get thrown outwards because they have less gravity being pulled at them, and so they're able to reach the outer parts of the solar system. Your heavier particles, your silicon, your iron, your nickel, your metals, they're going to be overcome by that gravity, they're going to be pulled towards the center. And so in our solar system and in many other solar systems, I'm sure when we actually get there, which you never know, you can see that the heavier elements are pulled towards the center. The lighter elements stay towards the outer edge, which is why we very much have two distinct categories of planets. We have inner planets, which are small, rocky, and metallic. You have outer planets, which are giant, gaseous super planets in a way. So as this continues, you're going to get the same thing that happens with your disk of gas as you did at the very beginning. Gravity is going to take over. The bigger chunks are going to have more gravity than the smaller chunks. They're going to start to suck everything in, and you're going to start to get rings, and the bigger chunks in those rings are going to start to pull stuff in, and they're going to form into planets, moons, sometimes small asteroids, stuff like that. But that is the general progression of the way the solar system works. I do have it over here with a blue background. You can see a little bit better. But this is our understanding of the formation of the solar system. Now, a couple things to add, and I'll come over here and kind of point this out. We really only have our solar system to look at. We do know of other planets. We do know of other solar systems, but we cannot see those planets. We cannot see them in a way that we see our planets and can interact with them. The only thing we see is the star itself. And if we're lucky, and if those planets are on a plane that corresponds with our planet or our solar system, what we might see is the planet come in between us and the star, almost like a bug flying in front of a headlight of a car that's pointed at you. And if you have an instrument sensitive enough and delicate enough to sense that, you can see the planet go in front. You don't really see it. You see the star dim, which tells you there might be a planet. And if you watch it for long enough and it dims over and over and over again in a regular pattern, then you can guess with pretty good certainty that that's a planet that's orbiting that star. And every time it dims, the planet is crossing across the star. And every time it brightens back up, the planet's not in between the star and you. It's on the backside or on one of the sides. And so our ability to really see planets outside of our solar system is not, it's not that we don't know. It's just we don't get a lot of information from them. And that's why when they talk about finding new planets, when they talk about second Earths and possible habitable planets, we don't really have a good understanding of what's there. And we may never. There's a couple movies where they go to try to find another planet and they get there and they're like, oh, this isn't going to work out. I mean, Interstellar is one of them, right? They go out to the other planets and they go to multiple different locations. When they get there, they're like, no, this is not going to be habitable at all. And that's pretty realistic. Our ability to see what's going on that far out doesn't really exist. So you can see this at the planetary level too, with Saturn. Obviously, Saturn's not a star, but the central body would represent the star. It has the most mass. It's pulled the most things into it. The outer rings would represent early planets. And in fact, some of the rings have turned into moons. Anytime you see a gap in Saturn's rings, there's a moon there. The reason there's a gap isn't just because there was nothing there. There was something there, but a moon that orbits around in that gap has gone by and like a vacuum has just sucked everything in with its gravity and cleaned up that little space of the rings. And so each of the gaps in Saturn corresponds to a little tiny moon. Not very big, but it's there big enough to pull in all the stuff that's around it. Which again is kind of something we're going to touch on when we get to Pluto. Pluto hasn't really cleaned up its area very much, which is the argument they're using to exclude it as a planet. But yeah, that's the way we kind of understand solar systems. That's the way we understand planet formation. And it kind of works the same way with galaxies. The early galaxies formed very similar to the solar systems, but instead of having planets, they were just all stars. So let me go back to the PowerPoint. They call the early stars protosuns. They call the early planets planetesimals, as they very much begin to form. Not quite round yet, not quite completely solidified. They haven't had the differentiation happen where, like in Earth, we have the dense inner core that's iron and nickel. All the lighter elements like silicon and oxygen have floated to the top and formed our crust. That hasn't really happened in the planetesimals and the protoplanets. It's still in the process of happening. Once that does happen, your planet really rounds out, which, by the way, is one of the criteria for being a planet. You have to be round, which means you have to be of a certain size where gravity is going to pull the larger things in and kind of smooth everything out. If you don't have enough gravity to be round, you're not a planet. Which doesn't apply to Pluto. Pluto is round. It's plenty big enough. But that is an important detail. So due to their surface gravities, Venus and Earth, which they didn't mention when we flipped through the other day, they called Neptune and Uranus sister planets. Venus and Earth are sister planets too. Very much alike. Couldn't tell it from today, but very similar size, very similar composition, and through study, we kind of believe that at an early point, Venus had very similar temperatures and atmospheric conditions to Earth. I don't know that we ever believed that there was water there, but our histories kind of went along the same path, and at one point, Venus diverged and got extremely hot, and the Earth is what it is today. The smaller planets like Mercury and Mars is a little different. We'll talk about that in a second. Mercury is too small to really hold in that atmosphere if it had one ever. And it's super close to the sun. So any atmosphere that Mercury ever had has long been blown away out into space. Due to the really cold temperatures, the Jovian planets, which are the big gas giants towards the outside of the solar system, contain a high percentage of ice, and their moons contain a high percentage of ices. So here's a nice little picture kind of showing our solar system. We'll talk about the Kuiper Belt later, but this is kind of out where Pluto is. And so kind of keep that in mind when I talk about Pluto and not really clearing its orbit, and us not really being certain that Pluto is going to be around in the way that it is for a long time. They have all the planets here. Note that we kind of have to exaggerate things. There's no way to really show the solar system as it is. The Saturn and Jupiter are not bigger than the sun by any means. And this one, they have the size of the planets correct, but obviously they're shrunk together so you can see them all in the same picture. The sun, very large, so large you can't even see the entire thing. Earth, Mars, Venus, Mercury, Jupiter, and Saturn are obviously the bigger ones, with Jupiter being the biggest. And then Uranus and Neptune out there. So you always have to scale things. You can't show the solar system in its true state, or it just look like tiny specks. You wouldn't really be able to see everything. Now we get into the planet designations. We have two groups. Terrestrial, which stands for Earth-like, like ET, extraterrestrial, means not from this Earth. Terrestrial means Earth-like. These are the four inner planets: Mercury, Venus, Earth, Mars. They're small, they're very dense, they have metals, iron, nickel, they're rocky, and most importantly for us, if you're into space like I am, low escape velocities. Earth, as I understand it today, and I could be wrong, we'll see how things go, with our current technology and the chemicals we've discovered on Earth, if it were too much bigger, we wouldn't be able to get off of it. We wouldn't be a spacefaring race. At a certain point, you get to a gravity level that you need an immense amount of energy or speed, as they put it, escape velocity, to get away from the gravity well of your planet where you can go somewhere else. And so for that reason, as of right now with current technology, if we ever land anything on these larger outer planets, that's not coming back. There's no way to get off of that planet with the technology that we currently have. If we land people on Mars, first off, the gravities would destroy almost anything we create. Maybe we could create some technology that survives it, but humans won't be able to step foot on these at any point in time. But when we send people to Mars, those people are likely going to want to come back. Whether they do or not will remain to be seen. But no one wants to go. Well, some people do, but most people don't want to go there just to die. They would like to come back to Earth at some point in time. That's not too hard. Mars is like a third of Earth's gravity, so it should be relatively easy to get off of Mars. If you go to something bigger than Earth, it's going to be even harder to get off of Earth or get off of that planet. It's pretty hard to get off of Earth by itself. When we send people up, usually we don't send much else with them. It's just the spaceship that has the people. We're not bringing like huge pieces of equipment or really heavy things along with us. And so our ability to take big stuff into space is really, really difficult. If you think about the International Space Station, the International Space Station isn't that big. It's basically the size of a football field. And we had to take it up in little tiny pieces over years and years and years. And so we are kind of at the edge of our capabilities as far as technology and fuel sources to be able to get off of this planet in a meaningful way. Now, the other planets, they call them Jovian, which stands for Jupiter-like. They're the outer planets, Jupiter, Saturn, Uranus, Neptune. They have low densities. They're mostly gas. They're very, very massive. I think Jupiter contains more mass material than all of the other planets combined, excluding the sun. Obviously, the sun's the biggest thing. But Jupiter is absolutely massive, super, super huge. They have very thick atmospheres composed of very light elements. Hydrogen, helium, which are the first two elements and the smallest and the lightest. Methane, which is, I think, 3 hydrogens and a carbon, maybe, or 4 hydrogens and a carbon, which is still very light, very small. And then ammonia. Somebody look up the formula for ammonia for me. I don't remember it. It's probably some sort of hydrocarbon issue, but it's going to be light elements as well. NH3, so nitrogen and hydrogen, yeah, very light elements. Where Earth has things like silicon, iron, nickel that are much lower on the periodic table. They're bigger atoms. They're much heavier. And then they talk about the high escape velocities. To get off of something like Saturn or Jupiter, you have to be going very, very fast to escape that gravity well. This is just a cross-section view of all the different planets, showing how the 4 outer planets are very different from the 4 inner planets. Earth and Venus, look at the size comparison. Very similar in size, very similar in the size of the core versus the size of the mantle. Where Mercury is much, much smaller, has a bigger core, which is more than likely molten. I don't know if they call it molten here, but Mercury is pretty hot. And then you have the Moon and Mars. I will note that Mars used to be pretty nice. It's not anymore. We believe that Mars used to be pretty nice, had flowing water. It does have ice caps now, so we know that there is water on Mars. We just haven't found any life that goes along with that. But at some point in time, probably because of its size and its distance from the sun, Mars cooled down. So it used to be hot. It used to have a much hotter core. It used to have volcanics. The biggest volcano that we know about in the solar system is on Mars. It's called Olympus Mons. It's very, very big. But at some point in time, it cooled down. The volcanics stopped. The core became more static, which means its magnetic field went away. The magnetic field is what protects our atmosphere from being blown away by solar radiation. So when its magnetic field went away, the atmosphere got mostly blown away. Note that Mars does have an atmosphere. It's not one that we can breathe. It's not going to keep us alive. But there's wind on Mars. There's an atmosphere on Mars. And if you send a spaceship there, you have to be cognizant of that so it doesn't cause any problems. The Moon has no atmosphere. It does have earthquakes, and it did used to have volcanoes. In fact, we're kind of believing right now that the first moon base will be in an old volcano tube. If you just put something on the surface of the moon, you can kind of look at it and see that the surface of the moon gets hit by stuff all the time. So if you put a base on the surface of the moon, there's a high likelihood that a rock's going to poke a hole in it and all your air is going to go out into space. And so if you build it underground, that's great. But again, we can't really take heavy machinery up the way we want to. So you're not going to be able to take like a tunnel digger there it's best to find a tunnel that's already there, like a lava tube, and live inside of that. So we'll see how that goes. That's still probably a long ways away, but we do want a moon base. And we'll get to that when we get to the moon. Your 4 outer planets here, mostly gas, gaseous hydrogen and helium, liquid hydrogen and metallic liquid hydrogen, which is theorized. We believe that it probably exists in there, but we've never actually seen or possessed metallic liquid hydrogen. Hydrogen is a metal, technically, but we've never made it into that. It requires huge amounts of pressure. And so, I don't know, that's like it's like a computer dream. If they could create metallic hydrogen, apparently it would be really nice for us to use as a construction material. But these are your 4 large planets. I will point out it's on this chart too, although they're really, really faint. All 4 of the gas planets have rings. Saturn's really the only one you can see with a Earth-based telescope, but all 4 of these have rings of some sort, where the 4 inner planets do not. Let's see. This is just a quick little map that shows the difference between the inner planets and all the moons versus the 4 outer planets. Very gaseous, very cold. Everything else is pretty warm. I mean, depends on your distance from the sun. Some of these moons out here, like Charon, is Pluto's moon. So very far away from the sun, pretty cold. Here's Pluto over here. Not a huge size difference between that moon and Pluto. Here's the Earth and our moon, Venus, Mars, Mercury, pretty close to the sun, nice and warm. So that's a neat little chart there. Okay, they're going to get into planetary impacts. We're not going to talk too much about this. The one thing I want to point out, when meteors or asteroids hit the Earth or hit the moon or any other hard body, it doesn't really matter what angle it comes in from. They don't really show the angle of impact here. But I watched this cool little video. Even if it comes in like from the side, like at a pretty steep angle, the crater is almost always perfectly round. And that's just a physics thing. It doesn't fit with how your brain thinks it should work, but apparently that's the way that it goes. Also, a lot of craters, not all, but most, have a peak in the center. And this is kind of like a physics thing. So first off, when there's no crater there, there's material stacked up on top of where the crater used to be. And that material is heavy, it's rock, it weighs thousands and thousands of pounds. It's pushing down inside the crater. And so when the meteor impacts, all of the material gets ejected out, including the material from the meteor. And I'll talk about that in a second. But all of a sudden, once it gets ejected out, this part of land used to have a bunch of stuff on top of it, and now it's not there. So almost like when you sit down like on a foam mattress, and then all of a sudden you get up, the foam rises back up because the weight that was holding it down is no longer there. The same thing happens to the rocks in the center. It rises back up, and it forms like this peak in the center. And so a lot of craters have these. We believe almost all of them. I think it depends on the size and the depth. Sometimes they get weathered away, and so older craters may not have them. But it's an interesting feature. It's also deceptive because some people early on thought that these peaks were leftovers of the meteor that hit them. There's a very famous story about Arizona's meteor crater. I forget what they call it. I might just call it meteor crater. There's this famous meteor crater in Arizona. It's the youngest one on the Earth that is exposed that we know about. And so it's the most recent impact. And a long time ago, this guy found it. And he's like, meteors are made of metal. This is a giant impact crater. In the middle, there's a bunch of metal, a bunch of meteor metal. I'm going to take my vast fortune and I'm going to spend it all building a factory and a mining facility. And I'm going to get me some metal and I'm going to sell it and get rich. And he wasted all of his money and he dug and he dug and he dug and he never found any metal. And that was kind of a lesson. I don't know if modern geologists knew at that time, but it was a lesson to us that the meteor does not survive the impact. It's not like buried down in the hole. It leaves with the rest of the ejecta and goes everywhere. You're more likely to find it scattered around here than you are to find it in the center. And so now it's a tourist attraction, and you can go down into the meteor crater and visit his, I don't know if the factory's still there, but yeah, he got it totally wrong. Okay, now we got to be careful of this. So if I ever get confused, just remind me. The topic will change sometimes, and they don't really give you a heads up. So we got to keep an eye on the title of the slides. So we're moving on to the moon here. General characteristics of our moon. It's a pretty large moon for what it is, and for our planet size, it's about 3,400 kilometers, 3,475. I think I've said this before. Most planets, when you stand on the planet, you won't be able to see such a large moon that's so close to the planet. That's just not a normal thing. And one of the reasons is how our moon formed, and we'll get to that in a little bit. The density is 3.3 times that of water, which is very, very similar to the Earth's crust. In fact, we'll actually get to it now. The way we understand the moon and its formation today is called the giant impact theory. And the theory is maybe there was a moon there to begin with, but at some point in time, a Mars-sized object, like about a third the size of Earth, hit Earth very early on before there's any life. There's nothing going on here, but it hit Earth, and just like we saw in the meteor impact, everything gets thrown out of the crater, right? So all that stuff gets thrown out into space, and it eventually coalesces into the moon. And why do we think that? If you look at the Earth and the moon, do they look the same? No. So when we sent the first space missions to the moon, and they took rock samples and they brought them back, we fully expected them to get to the moon and find rocks that were just completely different. We're going to be like, whoa, this is like moon rocks. They're crazy. They got there and they found rocks that are almost exactly the same as our rocks. They brought them back. We did tests to make sure. We chemically analyzed them. We named them. They're very, very similar to the Earth, which is not how we understand things forming. When you look at all the other moons in the solar system, they're not really like their parent planet. They have different materials. They form in different ways. But the moon is just way too similar to be a coincidence. And so the theory that we're working with now is that material, a lot of it actually came from the Earth in that impact. And that's why they're so similar. That's why our moon is so large and so close to us. And it kind of answers all the problems that we have with the moon. And so we do believe the moon has a small iron core, but mostly it's a lot of rocks that are very similar in chemical composition and in formation to the Earth's rocks. Here's the important part. The gravitational attraction is 1/6 of Earth's. This is why we talk about a moon base in science fiction. This is why NASA talks about moon bases. If you wanted to put up an International Space Station from Earth, you got to do it in sections. You got to do a lot of different launches. With the moon being 1/6 of the gravity and with no atmosphere, you could build something really big on the moon and launch it in one launch all together. And so that's something that really has a big benefit. And if we're able to do that, that would be one of the best things about a moon base is our ability to construct things and get them back into space, either to come back to Earth or to just be a satellite around Earth or to go deeper into the solar system. But yeah, if we're ever going to build like a, what's the movie where they wake up early? Passengers, yeah. If we're ever going to build like a big passenger spaceship, it's not going to be built here on Earth. The gravity's too much. We'd have to either build it in orbit or build it on like the moon, which would help because building things in 0G is pretty hard. If you have a little bit of gravity, it makes things much, much easier. The tectonics are no longer active, which isn't, well, yeah, plate tectonics are no longer active. The moon does have moonquakes. We left seismic recorders there that are still working today, I believe. So there are moonquakes. There used to be volcanoes. It's no longer active now, which means the moon's kind of cooled down. And yeah. So I already talked about the result of the collision. It's very early on, about 4.5 billion years ago. So really Earth was just starting to form. The solar system was very chaotic. There's probably lots of extra planetary bodies moving around in weird ways. And there was an impact, and the ejected debris was thrown out and ended up forming the moon. This model just answers a lot of different questions that we had about the moon. So the lunar surface, just standing here with no telescope, you can see different parts of the moon. There's dark parts and then there's light parts. The dark parts we call Marias, which actually goes back to before we actually knew what was going on. Maria is Latin for sea. So early on, they actually thought that there was water there. They were dark like the oceans. We know that there's no water there now, but they're the dark regions, and we still use that term, Maria. Fairly smooth lowlands. What they are is they're lava flooding. And so the dark parts are lava fields from back when the moon did have plate tectonics and volcanics. The highlands are the bright, really white stuff. There's a lot of craters there. They make up most of the moon. And in general, the highlands are older and the Marias are younger. And one of the reasons we know that is the highlands had the most craters, which means they've been around the longest and they've been hit by stuff. The Marias have less craters and less asteroid impacts. And so we believe they're relatively younger. Not like young, but just in general, relatively younger. So there you go. These are going to be your Marias. These are going to be your highlands. You got some highlands over here. You got a couple little Marias. If you've ever watched Apollo 13, if you haven't, you need to because it's an awesome movie. They talk about going over the Sea of Tranquility, and that is the Mare Tranquillitatis. Tranquillitatis. There you go. Tranquillitatis. Yeah, Latin. Is it Latin? Latin is not easy. But yeah, lots of different Marias. Also, a thing I will add, because I don't know if they're going to say it, the side of the moon that you see from Earth is the only side of the moon you have ever seen. The moon is tidally locked. It does spin, but it spins at the same rate that it goes around the Earth. And so the side that's facing us is always facing us. It will never turn around. The side that's away from us is always away from us. It's kind of referred to as the dark side of the moon, but that's not really accurate because it does get sunlight. It's never facing us. So the only people to ever have seen it with their eyes were astronauts that have orbited around the moon or landed. Although, for technology purposes, I don't know that we ever landed on that side of the moon because we had to have satellites and communication wouldn't have been great. So they talk about craters. It obviously has a lot of craters. Around the craters, you can see where rocks have been thrown out. And so it almost looks like a kid would draw a sun and you have the little rays going out. Those occasional rays are from little, rocks kind of skipping along the surface and leaving these gouges. Lunar regolith. Regolith just means like loose rocks and dust. So it covers all lunar terrains. We all kind of have this image of the astronaut stepping down and leaving the boot print in the dust, which most of those are still there. It's just gray, unconsolidated dust, usually from craters. Not from craters, but from asteroid impacts, kind of just breaking stuff up. There's not really weathering and erosion because there's no atmosphere. And so it's all from impacts. This is it says to chip off the old block, but I think that's referring to the Mars-sized body impact. This is just kind of showing the lava tubes. So an asteroid impacts, the impact melts some of the areas in the crack just due to extreme heat and pressure. And then you can have those cracks coalesce. Sometimes the lava kind of recedes and you have like an empty crack in a way. And then you see the nice crater in the center, and sometimes you have a ring around the outside where the edge of your crater was before. There you go. There's the moon. There's astronauts on the moon. There's the footprint that I was talking about. That's a really large rock, and I think while he was standing next to that rock, the guy next to him joked about him picking that up and taking it back to Earth. He's like, go ahead and collect that sample for us. They're pretty funny. Being in space would be crazy. John, the first guy on the spacewalk just basically like didn't answer NASA. They're like, hey, you need to come back now. Come back in the spaceship. No answer. They're like, hey, it's time to come back. Could you please like end the spacewalk? No answer. He's basically like, you can't make me, so I'm just gonna do what I want to do. And I think they were really like worried about him for a second. But so how is crater density used in the relative dating of surface features on the moon? Basically, if you have an area of the moon that has a whole bunch of craters, you know that it's pretty old because that didn't happen all at once very quickly. If you have an area of the moon that doesn't have very many craters, it's probably relatively younger because if it had been there for a long time, things from space would have hit it and you would have more craters. Nice. So we got through the moon. We will pick up with the planets tomorrow. We should be able to get through the planets in one class period, which leaves us Friday to maybe just talk about Pluto. So thank you for joining me online. I hope this video is helpful, and everybody have a nice day.